Hello and welcome to the third and last session of our Aerodynamics workshop series by SimScale and FRIENDSHIP Systems. Yes, I'm very happy to see again so many well-known names in the list of attendees. And yes, today we will put you into the seat of F1 designer. You will learn how to design very easily your own F1 rear wing. And yes, I think that's really a highlight of our workshop series. That really sounds cool, doesn't it? And yes, therefore, before we actually start to dive in our today's session, I would just like to make sure that everybody can hear me. So please, I think you know the procedure, click the raise hand button in the case you can hear me loud and clearly. I see some hands. Great. Okay, in the case maybe audio should break for you during the session, we also provide, as you know, a toll-free phone dial-in service. You can just use one of these free dial-in numbers, call them, and enter this access code, and then you will be able to hear the audio of the session through your phone. Okay, great. Then, yes, today we have our third session, as I mentioned, and the title of this session is Parametric Design Optimization. So, maybe as introduction, while in the last 2 weeks we were talking more about fundamentals and we focused mainly on what mechanisms are working on the F1 wing, how is the car generating downforce, and we also learned how to simulate this processes using SimScale. And today's idea is more to learn about a process and strategies how to improve the design of a Formula 1 car. And later on, as I mentioned, you guys will be able to design your own F1 rear wing. And as I mentioned, the idea of this session is really to put you into the seat of a designer yourself. And just as a rapid again, and this session or the idea of this workshop is really to deliver the fundamental of this session, and therefore we cannot talk about the theoretics of simulation. If you're interested in that, as I mentioned, there are a lot of good books we can recommend. I'm just saying that again because there was some question and confusion about things like y plus and dimensional wall distance, etc. And as you know, you can qualify for professional training by just submitting all 3 homeworks. 2 homeworks are left. The second one is right now open, and beginning of next week we will also launch the homework of this session. Okay, then I would say let's directly jump into the content since we have to deal with a lot of stuff today. And first of all, I would like to talk with you about the results of the homework of last session. I know some people are still working on you, therefore we will not talk only about the results, but about a lot of more things which were discussed in the forum. And one of the main questions was regarding the mesh resolution and the mesh size. And some of you asked if the mesh is fine enough or good enough for an accurate result. And first of all, I've created some more meshes and some more simulations in the meantime. Here you can see them. And the medium one is quite all of these meshes are finer than the one you are using during the tutorial. And as you can see, each of these meshes is finer. When we say finer, we're talking mainly about the regional refinement, not about the surface refinement. And you can see related values for drag and lift. And as you can see, after a dedicated point, this mesh here, which we called fine, there is not a lot of change anymore in the values. And this is what we call a mesh-independent solution. And to be honest, the tutorial was not a mesh-independent solution at all. The quality of the results is good enough to get some first insights, but if it would be really about absolute values, for sure you had to use a more finer mesh. The reason why we choose this more coarser mesh is that this is still a tutorial, and our aim was to deliver really the fundamentals of simulation that make you able to set up your own simulation, but for sure it is recommended, or it is possible to make the mesh finer. And just because I think some of you are interested, I've prepared some screenshot of this run, which we call dextrafine. So first of all, you can see a slice through the mesh. This is a symmetrical size, which is called in our simulation project bounding box 1. And here, for example, you can see some first changes I made. First of all, I added additional region refinement. I made both region refinements finer, and this one is dedicated for the area around the airfoils. And I choose it like it is because we need some fine mesh before we have our object and some more refined area behind the object itself to really solve all small vortices, etc. Then I added what you can see here, spherical refinements, cylinder refinements around the leading edges and the gap between the airfoils. The reason is that here we have areas where we expect the most changes, and especially this gap, as Akram mentioned in the first session, is very important because this gap allows us to let's say, use longer wings, longer profiles with a higher chord length, just because we bring new kinetic energy into the boundary layer here. And we also modified the layers, we make them thinner so that we achieved a Y plus an average on the surface from around 100. We also made one small change, just increased the edge refinement level for the edge refinement to 9, and this solved, by the way, all the issues we had with geometrical capturing. So this is something you can easily do also for your homework, but it's not mandatory from our side. Another very important point is, which was discussed and still is, for sure, the layers in the near of the wall. And here you can just see, for example, this is the cut in X direction. So this is the upper side, this is the lower side of the main plane of the front wing. And here we can see this separator in the middle of the wing. And here you can see the layers. And as I mentioned, you have this logarithm growth of the height of these elements. And you can see how good these layers are. They are really following the whole surface. And here we have a detail where you can really see how it's expanding. And here again a screenshot from the layers. This is at the leading edge of the main plane. Here you can see again the quality of the layers. They following really the whole surface and are really really nice. Okay. Then, for example, here you can see the velocity distribution in this main plane and the edge of the cells. And here we have this point by the stagnation point, by the way, where we have this pressure coefficient of 1, the highest static pressure. And then let's take also a look at the velocity distribution for the whole wing. Here you can see a separation here and a separation here. And to solve the separation, by the way, the layers are essential. Yes. Okay, and then we have also the Y plus values visualized here. And as you know, Y plus is very important for having the right modulation of the boundary layer. And here you can see the different colors are for different Y plus value on the surface of the rear wing. And maybe first of all, one of the most important things is that Y plus for using this turbulence model K omega SST should be below 200, but not below 1. So we need a value between 200 and 1. Otherwise, we can get some trouble later on when using the simulation to predict something like, I don't know, stall or forces. Another very important thing is that when looking at your mesh and investigating Y plus, that you really don't forget that even a small area having higher Y plus numbers can really cause a lot of problems. So therefore you should be really careful about this. Okay, then We have some other things we can take a look at. And I mean, I don't want to get too much into details because this is still a part of the homework. But what is you can see here is a slice through the in X direction at the position where we can see this loop with the slots on the end plate. And what we can see here is the velocity component in Y direction. Y is right from our view, so in this direction. And here you can see that in this direction the flow is leaving leaving this part in the inner part behind the end plates with like here we have like 40 meters per second in this direction. This is for sure just in Y direction, so the magnitude will look different, but this is for sure the role of this louvres, that they allow air with higher pressure, which we'll see later on, to leave. And this will reduce the overall pressure at the upper side of the wing and reduce the drag and increase efficiency. Here we can velocity component on that, and that show you, and I mean that's correspondence for sure, the flow is going in this direction. So therefore we have a high component in Y and a high component in Z. And here we can say a vortex created by the wing and by the louvre here. And this is pressure distribution. Here you can see it's a high pressure inside, low pressure outside, and here we have this transition area where, transition area is the wrong word, but here we have this area where the pressure is, or the high pressure area is leaking a little bit outside. Okay, guys. Well, do you have already some questions you would like to discuss with me? Akram, can you hear us?
Hello? Yeah, I can hear you. Can you hear me?
Yes, we can hear you very well. Thank you very much. I will just make you to the presenter.
And you can see my screen now?
I think you have to share it.
Okay, perfect.
Yeah, now we can see your screen. Thanks.
Okay, great. So, good morning, good afternoon, good evening. Welcome again to this series of webinars between SimScale and Friendship Systems. So today is the last session. We will cover parametric design and optimization. So also we will have a session about software, our software at Friendship Systems, called CAESES, and we will see in demo presentation how to work with this software. So let's start our presentation. So for today we will talk more about designing and using a CAD design, and like we have covered in the first session, Formula 1 F1 teams, they have like really big CAD design offices and design offices in generally, so they invest a lot of time and money in these offices to make it like really really efficient to design the parts and also the car. So here in these pictures we can see some of the design models and also the offices in the F1. But the idea is when we see the design here, we see the 3D design, but in fact this design is based on 2D scratch, and this 2D is really like curves and lines, and these lines are designed using parameters. So let's see this here. So let's discover what's the parameter and how this parameter can be later controlled. If we see from the left side, we can see this airfoil. We have already talked about the airfoil and the role of the airfoil. So if we talk about the design of the airfoil, if we take, for example, here like the NICAP 4-digit, so we have 4 parameters that control the airfoil. We have the chord length. We have the chord length, it's the distance from the leading edge to the trailing edge. We have the camber, or the maximum camber, which is the distance between the chord length and the chord line and the camber line. Also we have this thickness and the position of the camber. So it's from the leading edge to the position where the maximum camber is. The idea is, imagine like you have this 4 parameters, and these parameters can be varied, of course. So you can take the length of 1, 2, 3, up to, so you have the chance to to change these parameters, and imagine how many configurations you can generate using these 4 parameters. So you will have an infinity of designs using just 4 parameters. And in Formula One, or in like more complex things, because the airfoil, it's really simple because we have just 4 parameters. But for like more complex things, like for example here, this from the right side, this picture here of the front wing of the Perrine model, where we have seen this in the last session with the last webinar, the last year with Nicolas Perrine, where he showed us this model, and we can see here that this we have 4 airfoils, and for every airfoil, like we said, we have 4 parameters, but not only parameters here, but also for the gap, the distance between the airfoil, the overlap, how the distance between here the end plate and the profile. So all these parameters, so all these lines, all these numbers are parameters. And imagine how much design variables or design configurations we can generate using these different designs. So this is what we will discover in our presentation of today. If we have a look to the design of Formula One, and let's talk a little bit about the front wing, because it's really complex geometry, especially with the new regulation. If you see the picture from the left side, it's the picture of the 2010 Mercedes F1 car, and if we compare it with the car from the right side, it's the 2015 F1 car, and we can see that there is, you can't imagine like it's from the same team, because like you can see here, the geometry is really simple. It's just like 2D extruded model, so just like we have seen this profile extruded along the path and cut it from here, and we have just 2 elements. The end plate is quite simple geometry, also the cascade elements. And if we talk about the same, what I have showed you, like this section where we have these lines and everything, we can say that this model here is designed using maybe 100 design parameters to control all the design, like for the end plate, the gap and everything. But if we talk here about this new model, seriously, it's about maybe 1,000 or more parameters. So imagine like you have 6 elements here. For every element you have maybe 4 or more parameters, because generally in F1 they use their own airfoils. So imagine like maybe they have 6 parameters per element, per profile, and for 6 elements here, and the gap and the overlap, also the position here. So the complexity is really high. But how they have reached this point, from starting from this simple design to here, it's all about understanding your design space. So you have a design space like we have seen before. It's this FIA boxes, and this is your design space, and you have the freedom to design inside. So by using space design exploration, so you will understand how your design space is so how your design, how your space you can design inside. So if you can see here in these pictures, we will talk just about the nose, which is, compared to the front wing, is really simple geometry because it's just like a cone. And if we take here, we have 4 parameters. So we have the nose height, so from the ground maybe to here, to the leading edge of the nose. We have the nose thickness. As you can see here, this is the second parameter in the design. So here we have the thick one, thin one, and here we have the length. It's from this this plan here to here. So you can see for the minimum parameter value and the maximum one, and also we can see the width. Imagine just with 4 parameters how many possibilities you can design. So we will have infinity of designs that you can investigate, and to facilitate these things, there is softwares and there is techniques to facilitate this using some algorithms and we will discover this in the next slides. All right, so now we have talked about Formula One and design and how you design in Formula One and understanding what is parameter in design. So now let's talk about cases. As you know, for this webinar, it's collaboration between SimScale and Friendship Systems, and here at Friendship Systems we are specialized in development and selling software called CAESES, specialized in parametric CAD modeling and also optimization, and we will discover this. Okay, so just a few words about what is Friendship Systems. So Friendship Systems is a German software company based in Potsdam, Germany. Our passion in the team is to develop a software called CAESES. So our target is simulation engineers, but only anyone who is interested about the intelligent surfaces, so like you will see later in the few slides. All right, so now let's talk about the workflow, because we said that you can like generate different geometries, but of course these geometries need to be tested to evaluate the performance of every model. So in CAESES, all this workflow is integrated in one interface. So what we do here with CAESES, so just first thing here, it's the CAD upfront CAD. What we do, we have our own CAD packages, so you can design whatever you want. So of course, design that destined for flow analysis. So here we have like capability in designing a CAD model, but not only a simple CAD model, parametric CAD model, and this CAD model also will be tested. But due to this large number of possibilities that you can test, we have an automatic way to test all your designs using CFD, and we have the possibility to integrate any software, CFD software with our software to evaluate automatically all the design variables. And these design variables will be generated using algorithms. So we will talk about this later also. And also we have post-processing. So you will get like all the results, all the plots that you want. So it's a really integrated way to evaluate your designs. So this technique of parameterization, of course, we are talking about aerodynamics, but also aerodynamicists in Formula One, they don't investigate only the external aerodynamics of the car, but also cooling the engine or the engine intake, or also cooling the brakes, and like these things are integrated in Formula One development. So here's some fields that you can apply this technique of parameterization and automatization of the development process. So for example, in the engines, also external aerodynamics for the exhaust and the pipes, and like the cooling system and turbochargers. So we have a lot of domains that we can cover with this technique of parameterization and optimization. All right, so now we have talked like in brief, I have given you a brief overview about what is CAESES. So now let's talk step by step, every step, what we do in every step. So here we have the workflow. Like I said, we generate a CAD model. Of course, this model here is from the Perrine models. It's the LMP1 model. So we generate model, or even you can generate like an isolated part, like for example the rear wing, or this fins here, or maybe another part. Then you will like generate, like you can see here, this mesh, not CFD mesh, but I'm talking about surface mesh. And like we said, that this software, our software CAESES, can be connected to any CFD software. So we have this step of software connection where you can just like run first simulation, take the control files and use it in CAESES to automate the CFD process, because like I said, you have a lot of design variables and you can't do it. So if you do it, you will take a lot of time, but it's good if you do it automatically to reduce the time and the cost. And then we have post-processing, so we will visualize and you will specify, for example, which quantity you want to visualize, and you will get results for all your design variables. And also we have the optimization, so understanding how these parameters behave, how these parameters affect your targets. And so if it's, for example, downforce or drag, how, for example, the camber or the camber position or any other parameter can affect these targets of drag and downforce. All right, so let's talk now in more details about the CAD modeling and our way in designing using CAESES, because that's right that we have the same way of design with, like, for example, the other software. We have approximately the same tools, but we have some capabilities, especially like we will discover later, what we call it the meta surface. It's our technology where we have developed it here, and it's really a tool that can allow you to design some really complex geometries in a really easy way and control it with the just few parameters. All right. So here, the CAD, like I said, is approximately the same like other CAD softwares, but generally when you do this technique of parameterization and changing the parameters, you need to get a software that is really robust and generate a CAD model that is really robust, and even if you change some values in the parameter, you need to make sure that your design is still feasible. So this is exactly what we are doing here with our software. So also the surface that is generated with CAESES, it's like really clean surface that can be used directly in the CFD, and also the quality of the surface, you can control it like we will see later in the demo presentation. And like also this is a really important point, is the meta surface, because this surface is really smart and can be controlled with some functions. So it's unique tool compared to the other CAD softwares. And also we offer like multi-strategies like fully parametric modeling, so starting from scratch, starting from the 2D plans drawing, and also you have like the partial parametric modeling where you have like already a model and you apply some techniques to modify the geometry, but you will not redesign the geometry, it's just modify it. So we will talk about this in the few next slides. I have already talked about what is the parameter in the design. So the parameter in the design, it's a value that describe like one length or a radius, or so it's a value. And here if we take this example just to show you our technique of the meta surface. So here, let's say that this is the upper side maybe of an airfoil. So we can design this curve here by this parameters, which is the chord length, and also the P2, this red parameter here, which is maybe the core, maybe the thickness, maximum thickness, and also the camber position. So these are two parameters. And then this parameter is just in the 2D plan, and of course we need 3D. We need 3D model. So here we have what we call it these functions. These functions are functions or lines that describe how these parameters behave along a span or along a path. So imagine like we have in the front wing this. From the front, if you see it, so we have in the span-wise, for example, the characteristics or the parameters of the wing are changed. So to do this in the classical CAD modeling techniques is to create different different sections and then loft these sections together to get this shape. But here we design only one section, then we have these functions that describe how these parameters change along the span. And if we do this, so we will have what we call it this, the meta surface, or this surface that is described by the profile parameters and the functions that describe how these parameters behave in the span Y. So like you can see here, and every section from these lines here are described by the intersection of the function with these values here. So this is the meta surface technique. And let's give you some examples, because I have talked more about the idea of the meta surface, but I'm sure when you see how this surface work, you will understand more the idea. So here we have Formula 3 front wing, and this front wing is fully parametric model and is designed using the meta surface, and we will see how it's designed in the next few slides. So like we said, the first thing is to start with your 2D profiles, or because we are talking about the front wing and the wings, so generally you start with the airfoils. But if you are talking about another thing, of course, you have another things to take in consideration. But let's focus on the front wing of this Formula 3 design. So here we have the airfoils, and these airfoils are controlled by the following parameters, such as the maximum camber, camber position, thickness, leading edge angle, the trailing edge, radius, etc. So we have a lot of parameters, because like you can see here, these profiles are not like the NACA 4-digit airfoils, but are like our design airfoils. Alright, so like we said before, so these parameters later will be connected to functions that describe how these parameters behave along the span-wise. And we can see here for the left side, we have these functions. These functions describe how these parameters, and like you can see here in the middle, we have these colors. Every color describe specific parameters. So for example, if we take this blue here is the camber. So this line here describe how the camber is developed along the span-wise direction. All right, so we have these functions, and when we connect our 2D profile to this function, we get the surface, like I have showed you in the previous slide. So here we have the path of the elements of our front wing. So here we have the elements, the path for this flap here, and here we have the path for the main wing. And if we see now, it's fully parametric model, and the idea is, so if I will back just 2 slides here, these functions here, like I said, are control these parameters. So the idea is, if you change this parameter, so like you can see here, we have these points here are point of control. So we have here in the start, the end, and also we have here. So these points are point of control that will control the shape of the design. So later in the demo presentation, you will see that just moving this point will affect the design. So this is how this design now is moving. So like you can see, we can see like that the chord length is changed, so the camber position, also the angle of this element here, the flap. So it's really fully parametric model. Also, this technique can be applied, so we can use it in many different parts. Like for example, here we have the same technique of meta surface applied on the rear wing. And here we can see our rear wing, and here we have the functions. And here is more nice, because we can see when these functions are moved, or this point are moved, this shape here will will be dependent on this function. So like you can see when we increase the camber, so this one, it's the main wing camber, and just when we move these points, this geometry here will be affected by these functions and will follow the same distribution as in the functions. Also we can see the thickness, these functions here, the yellow one. So you can create different distribution depending on what you need. For example, if you have a point where you want like more downforce, or you load your wing more, so just you increase a little bit in the core of the camber, and also maybe a little bit in the thickness. So it's dependent on what you want. Also here you can see, so by moving this function, which is the flap chord length, you will move this element here, and we have already talked about the role of this cat here. What is the role of this cat is just to like make sure that you will not have deviation flow in this region due to this gap separator element. Good, so now we have talked about the first technique, is creating a fully parametric model and control it by parameters. Now we are going to talk about the second way, or the second method of parameterization, which is the partially parametric modeling. And the idea is starting with already existing model. It's not a problem if it's model created with another software, so it's not a problem. Just bring your surface in the software and apply this technique of freeform deformation. So the freeform deformation, it's an approach that so you will just create these boxes. If you can see here in details here in this inlet, the engine inlet, also the rear wing and the front splitter. So we have these boxes, and the idea is that these boxes, I will just explain the idea like easily. These boxes are connected to the position of these boxes are connected to the position of the triangles of the surface here in the geometry, and when you move this points here, also the geometry triangles will follow the points here, and we will see this like here. So we have this tube, maybe it's like the brake cooling duct, and using these boxes you can morph or you can change the geometry like you want. So this is partial way to it's partial way to parameterize your model. Okay, so we have talked that we have created this box here, and you can see here in the animation the possibilities that we can create using freeform deformation. So we can make it more large, more, so for example, I will give you just an idea in design here. So if you have, for example, a race where you have like your throttle is always, I mean the driver is always the throttle, so you need to make sure that your engine inlet is really large, but of course to get maximum air to the engine. But for example, if you have the circuit where the throttle is not really high, so maybe you can make it more smaller like this to make sure that you will reduce the drag, and it's dependent on your targets in on the design to get your performance. Here also in the rear wing, so you can change the angle of attack, or also the camber, just by moving this point, just by changing the position of this point, all the geometry will change. And here also an interesting point is in the front splitter. So you can change the twist, you can twist your wing, or you can change the angle of attack completely like here of the second element of the splitter, and also you can increase this height between the ground to and this element. It's dependent on your target in the design, so you change this geometries. All right, so Also, the last time we have talked about the FAA regulation, and it's really important, especially here in this kind of design, the parametric design, to make sure that your design is always feasible and always is under the regulation, because it's possible to create parametric model, but this parametric model will behave in a way that is not legal by the regulation. So for example, you can design a front wing, and at some point if you run your optimization, for example, the chord length is larger than the box, and you will test some models that are not legal. So for this reason, with our software CAESES, you have this possibility of putting constraints. And the idea is to put some like some functions to describe, like for example, this point maybe in the leading edge need to be always lower than a value, or maybe you can also create a box, and just when this geometry will intersect with the box, you can say that this model is not legal, and you can test it later in CFD. So this is a really important point, especially in Formula One, because like you know, Formula One is not only regulated by the FIA regulation, but also with the time spent by the engineers in the designs, especially in CFD and wind tunnel. So we can't run CFD tests where in the end you will test some illegal designs and you will spend too much time in something wrong. So this is a really important point to create these constraints to keep your design always feasible and under regulation or legal. Okay, perfect. So now we have talked about this technique of creating model, even if it's so you can create fully parametric model by starting from the scratch and your lines, or you can modify your model or the existing model, like we have seen in these few slides of the LMP1 period model, where you have the model and just apply this technique of morphing and form deformation, and you will change the geometry in the way that you want. Now, because we have this different design variables, so you will have, I don't know, maybe 400 or more design variables, we need to test these designs, but it's really impossible in a way. So it's possible, but it's really difficult to test more than, I don't know, 400 maybe or 500 design variables. So for this reason, we have this capability of software connector. So what we do here, we run our CFD, we run CFD test for one model. Then we get like some journals and some files to control like the automatization of the process and put it in CAESES. Of course, you have to put the geometry, and also you put your output. The idea from the output, it's the results. So if you want, for example, to evaluate the pressure drop, or for example the drag of the car or the downforce, so just you will like put a report that you want for every design. You get a value for maybe downforce, and then when this process is done, you will have like long list of your values for every design, and just to check where is the best design. So this point here is the software connector, where you connect, like I said, any software, CFD software I mean, with CAESES. And now it's a really challenge for us to get a way to connect SimScale to friendship system for CAESES, sorry, because it's web-based software, but we hope in the near future we will find a way to do this, to connect SimScale and do this process automatically. But of course, it's possible to do it manually. For example, if you have, if you don't have too much design variables to test, you can do it manually with SimScale. So we will show you this later in this demo presentation. All right, so now we have Design Space Explorer. like we said, you will connect your software, and now we are in the stage to test many design variables. And here it's possible, for example, to say, let's take, for example, a parameter. If you remember the idea of this nose, we have 4 parameters. Let's say, for example, the height of the nose starts, for example, the minimum value from maybe, I don't know, maybe from 30 to, or maybe from 10 to 30, and you will say that I will change this by 1 step, 1 millimeter or 1 centimeter every time, and you will get like really regular modification in your geometry. But the idea is there is another way to do this by using algorithms. So algorithms that you will put your design variable, your design variables, and this algorithm will do like the connection, or not the connection, the right word is will check. We'll take different values from different designs, arbitrary, and we'll create arbitrary designs. So this will give you more chance to cover cover your design space in really quick way. And there is different algorithms, and of course at our software we have different algorithms. And also, if you want to learn more about this algorithms, we have a good documentation in our software, so you can check it. Like I said, so here we have our, so here in the lower side here, we have our parametric model, let's say. Using this algorithms, you will generate different geometries. So like you can see here, different possibilities that your design can be. So it's up to the algorithm to generate this design. Then automation of the process. So for every design variable, you will run a CFD case. And of course, for every CFD run, you will get back some results that you specify, for example, drag or downforce, or I don't know, any physical variable value. And this, and also we will have here, you can see in these plots, you will understand, depending on the parameters and design variables, how your parameters behave. So how your parameters affect the results, and you can generate post-processing and so on. Here it's really interesting point that I want to show. So this picture is taken from this paper here. So you can just search this on the internet and you will find it. And the idea here is really nice to show you how to cover your design space. So what we have here, we have this dot here. It's the baseline. So this is the first design idea. And we will evaluate, and the idea is every point from these ones are design variable. So modification in the design, I mean modification in the parameter. So this parameter maybe the first time, let's assume, for example, this is a rear wing. Yeah, it's a rear wing design. So for example, for the first time we will change in the chord length maybe, and we will have this design. Then we change in the camber, we'll have this design. So we'll have different designs, and these designs will be tested in CFD, and we will get this result. So we have here the drag force, and we have the downforce. And of course, if you do the ratio between downforce and drag, you will have efficiency. So here we can see the different designs, and this is the baseline. And the interesting thing is just from one run, so just from using the first run of optimization, you will get different design categories. And like we have talked in the first presentation, in the F1 session, we have we have different circuits. So circuits where you need high downforce, circuit when you need low downforce, so you need more speed circuits where approximately the most almost all the circuits approximately are medium circuits. So we will have already from one optimization run different candidates for high downforce or low downforce or even for medium downforce. And you can evaluate this using the, so here if you can see here these designs here are for high downforce, are the high downforce family because they generate maximum downforce but with maximum drag. And like we said, for example, in Monaco circuit, you don't need too much, you don't care too much about the drag because you are interested more about downforce. So for example, you can take one from these designs for Monaco, and here, if we see here, sorry, so here we have low drag with approximately low downforce, and this is exactly what we need for high-speed circuit like Monza because we need to make sure that your car is really fast in straight lines and you don't really care about the drag of the car. I mean downforce, sorry, because you have only straight lines. And here it's the medium downforce family where the efficiency it's really high. So if you do the ratio between this one and this one, so this family here it's the family with the high efficiency. All right, so many thanks for your attention. I hope this presentation was helpful for you. Of course, if you want any questions or just you can contact me here on this email address. And no, it's not the end, but let's go to, so first I will show you from where you can download, from
Akram?
where, yep.
Maybe it's better
Hello?
that we first introduce the homework and then you can show them where they can get cases
Okay,
free.
yeah, for sure, for sure. Thank you so much.
Okay, great then. 1 second, guys. Can you make me a presenter again?
Okay,
Oh wait, I can do it myself. Okay,
that's
guys.
okay?
Great. Can you see my screen?
Yeah, perfect.
Awesome. Yes. Thank you first of all, Akram, very much for this interesting presentation. I was very fascinated when I heard this the first time, which powerful tools are existing there to modify designs.
Okay, thank you so
And
much.
yes, first of all, yes, I think we should now talk about your homework because your homework for this week will be very challenging, exciting, and for sure related to the subject Akram was talking about, because we will put you into the seat of F1 designer this week, and maybe as an introduction, you will be provided with access to a software which is called CAESES Free. CAESES Free is a tool by Friendship System which allows to modify and parameterize models. And we will provide you with the ready-to-use model of a rear wing, and your job will be to modify it very easily with a few clicks, like Akram will show you later on, and then simulate your rear wing using SimScale. And then you will, like the last 2 times, submit the link, project link, and this time you will also ask to submit the forces which are generated by your wing. You know how to measure them by using the result item. And yes, we will also in a few days put again put online step-by-step instructions, and there you will can also read all the details regarding this challenge, like how to modify the model, where to download cases, where to download the parameterized model, and so on. Yes, thank you very much. And now Akram will just show you how to modify the model.
Hello? You
Hi,
can,
Akram. I will make you presenter just 1 second.
okay, perfect. Okay, you can see my screen now.
Yes.
Okay, perfect. So let's start. So first of all, to get the free version of, so CAESES, it's commercial software, but we have our free version. So the free version, you have approximately all the functions as the professional one. So we have some things that are not the same, like for the optimization later, you can't like run all like all the variables. I think it's only 5 variables that you can change or something like that, but we don't need the full version for our assignment. But also we have student version, so if you are a student and you want to do your thesis or something like that, so you can contact us when we can provide student license for student. So I would like to show you from where you can get our software. So just you can Google it on Google. So just CAESES. So it's CAESES. It's CAESES. All right. Then here is our website. It's caeses.com. And then this is the main page of our website. So here we have two, so if you go to products, you have CAESES and CAESES free. So what you want to do now is to get CAESES free. So here when you click on CAESES free, you will see some pictures, and here it's the difference between CAESES free and CAESES commercial. So it's the idea, if you are so you can also use CAESES free like for commercial use, and also the upfront CAD, it's the same. So if you want to design something, it's the same like the free version, like the professional one. Upfront CFD, so connecting the CFD to software to CAESES, it's completely the same. The main difference is in the optimization, because you can't, like I said, evaluate too much the designs using the free version. So to download, so free downloading, so just if you scroll down, and here just when you click here, you have already a Formula One here, and you have different like download, so you want the 32 byte or 64 or even Linux. So just it's dependent on what you want. So just you click here and you will get the version, the free version. Okay, that's perfect. So now we have talked about how to get the software. So now let's say that you have downloaded the software, and let's talk about the software itself. So maybe I should start from zero. Okay, so here it's the interface. So just to give you a quick idea about the interface of the software, this is the interface of our software CAESES. So what you have here the CAD. So here in this bar you have a file where you can import open projects or import geometries, or also export or save. So it's the same in all the software. So here we have a CAD. The CAD, so where you can generate points, where you can generate curves, and you have this library of different possibilities to design. So we have different definitions of the curves, different definitions of the surface. So you have all the possibility to do what you want. Here we have the BREP or boundary representation. Also, you can create really high quality surface mesh, I mean not surface for CFD, but I'm talking about like STL or surface mesh. Here its transformation is when you rotate, it's operation, so when you rotate, you translate, you scale everything. Here we have this really powerful tool to design the blades and the propellers. Yeah, you can discover this in our documentation I will show you. Okay, so here we have the software connector. So here where you can connect the CFD softwares with CAESES. And here you have the optimization, and like I said, we have different algorithm of optimizations, and also we have the Dakota where you can get different algorithms. So here its visualization is more later for to create like pictures, a frame, give pictures, animation, and so on. Here is to create features, so to create your own like script to like control something or to create something. Here it's view like zoom and so on. So that's good. So now so this was just brief and quick overview about the interface and what we have in different points. So just we will open our model. So here is our model. This is the same model that you will work on during your assignment for this last session. Okay, so for the first time when you see to this wing here, it looks like really the same like the one of Pirim, but we will see this later. So just a second, maybe it's a little bit slow. So here this model, so just how to move it, so I will give you just a quick overview. So just to rotate it in this way around an axis, so just by clicking on the right side of the mouse and keep clicking and moving this way. So translating it by clicking, translating this way is by clicking on the wheel of the mouse and do this. And zoom in and zoom out by the wheel. Okay, perfect. So in fact, this model, like I said, from the first view, it looks like the same of the Pirim, but it's not, because here what we did, we have imported the ender plate. So if we see here, this ender plate and also these louvers or these slots here are created with, it's the same model as the Pirim model, but what we did, we have created a parametric model, I mean fully parametric model for these two elements of the wing, I mean the main plane and the flap of the wing, and also the gap separator. So these elements are modeled using CAESES and are parametric models. And here if we see the tree, so here we have the boundaries and we have the parameters that describe our model. So just if I can show you some of the parameters, so we have the core length, the camber position, like we have talked before. So these design parameters of the 4-digit NACA profile are here, and just because we are talking about the NACA profile, here we provide models for an NACA for 4-digit, and I think this one is the 6-digit. So you can just click here without designing the profile, just click in here and you will play with the parameters of the airfoil. Okay, great. And also, like I have said before, this technique of the meta surface, because this wing is created using the meta surface, so this parameters here are connected to these functions. So here we have functions, so for the wing chord length, so every parameters from these ones here in the top is described by these functions. I mean describe it along the span-wise of the wing using these functions, and I will show you now these functions. Okay, so this is really important I think for you, because to do this later in your assignment. Okay, so to see the functions, what you have to do, in fact the functions are just right here. So what you have to do, just go here to overview, and you can go to this one and select it, because here is deactivated, like you can see it's not blue. So just click on this and you will get the new window here in the bottom side. So this window here we will visualize our functions here. So our functions are already here but are somewhere, I don't know. So just to get your functions, just click on this zoom selection. Sorry, I can't find the functions, just a second. Oh, yeah, that's right. Okay, so the functions are here, and what we will do here is just to hit this surface to get only the functions. And what we will do, just, all right, that's great. Okay, so here we have the functions, and like we said, every parameter from these ones is controlled by this. So just to zoom here and to show you how this model will behave when we change in the functions. Okay, good. And like we said, these parameters are controlled by this function. So here we have this function with the purple for the wing chord length, we have the flap chord length, and so on. And like you can see here, these functions are like straight. So there is nothing to see here. So it's just like extruded 2D profile. But what we will see now, for example, let's take one of these parameters. Let's take one that have an effect, visual effect, so main wing camber. So what we will see, we will try to change the design here. Just like I told you, this point, so here for example, it's really too much. We have 6 points, and the idea behind 6 points is just like, imagine like just the half of your wing is split it into 6 sections, and for every section we control it with one of this point. So let's, for example, if I select this function here, these 2 points, okay, and if I will change, you can see on the top how the model is moved with this function. So like I told you, it's the meta surface. So you can increase or decrease in the camber depending on what you want. So for example, let's increase it a little bit like this, and we'll also try to change in the other functions. Maybe a function that also have an effect, maybe the thickness. Where is it? The thickness. The thickness is this yellow function here, and also let's control the same 2 points. And you can see on the top window that this thickness is controlled by this function, and when I move this function, the function points, also the geometry is changing depending on how I change the function. And this is really good. It's a really powerful tool to design, because imagine, for example, that you have this design and want to optimize this region. To do this, like for every iteration, for every, design variation, you go to the CAD design and modify it, and this will really take time. But here you can see it's just by 2 clicks on 2 points up, and you will have new geometry, and this will not take even time to update. So it's really on time. So just moving the point and you will get the geometry. Okay, perfect. So just let's say, for example, this is my best design and I want to test it. Like I told you, now we don't have the possibility to do the automatic process with SimScale, but we can like export this geometry as like a separated model and run it separately, so design by design in SimScale. How to do this? So here we have just from here, if you go to File on the top, then Export, and you will have different formats to export. So STP, IGS, or STL, and even for STL we have different STLs. And for your assignment, what we will do, we will use the STL multibody, because what we want like an STL with different boundaries to evaluate later, for example, the forces on every part. It's really important. So remember, and I will also put like later a small tutorial on the forum how to do this step, so don't worry if you missed any thing, no problem. So here exporting using STL, but a really important thing, especially for CFD, because in CFD we want to get like because I will show you if we adjust a second, if we go like here in close, and we will see how these boundaries are represented. So you can see are represented using triangles, okay, so using lines. In fact, this model here is really, I have increased the accuracy of the model, but in case if you have like low quality model, so just you can, I'm not sure which model Milat will provide you later, but I will make sure that he will provide you maybe this model to facilitate the things for you and to not go through this process of increasing the resolution of the surface. Okay, that's good. So the idea is just by moving the functions. I hope it was clear for you, and even if it was not clear, I will do like last change. So like I said, just make sure that you have the 3D overview here, and you will have this function. This function just you can see that are in the x. So just you click on the x direction or the x-axis, and then let's take one other, like the last modification. I don't know which one. I will try with the main wing chord length. So if we change the main wing chord length to make sure that in the parameter that this gap and the overlap will stay constant. So when we change this chord length, also the flap will change. So let's try maybe with these 2 points here from the outside of the chord length, and we will see modification in this region. You see that it just moving a little bit your functions, and you will have like really smooth and nice geometry. Okay, great.
Akram?
And to show you, yep.
Sorry, can you maybe show us also how to export this model into a STL file?
Yeah, for sure. So the idea to export it like an STL file, and like I said, make sure that you will import like multibody. I think it's more helpful for you later. So what you do, just file, and then go to export here. So file on the top, then you go to the middle here to export. Then you will have different formats, and for our assignment, just make sure that you will do multibody. And when you click on multibody, you will specify where you will put your model. So just let's create new folder. Maybe we'll call it SimScale model. And here you will call it like, for example, rear wing. Maybe this can take some few seconds to, because like I showed you, it's really high resolution surface, and like you can see here in this comment window that we have nine objects exported, and they are the same elements here. Okay, so this is what you have to do, just move in the functions, exporting, and if you have missed anything, make sure that we will provide you a tutorial step by step how to do this. Okay, Milad, it's for you now.
Great, thank you. So
yeah, we're all welcome.
Now there's time now to answer all your questions. And give me just 1 second. Great. Okay, guys, we have some questions here which I would like to answer. First of all, a question by Thomas. Is there any recommended maximum jump in the mesh element size from refined region to adjacent causal one? Yes, that's a very good question. And first of all, yes, there is a kind of rule or something you should consider at least, that everywhere where you have a change in the mesh size, that this will have a negative impact on your result. There are some effects like numerical diffusion, which will make your or which will decrease your accuracy, your local accuracy in these areas. On the other hand, you gain a lot of accuracy for sure because of the adapted finer mesh. And so, in general speaking, I would say there is maybe not more than 20% growth per element. But for example, when using SnapPX mesh with the predefined settings, there are automatically layers added so that the transition between the mesh sizes is very smooth. There's a next question by Deepak, and he wants to know what the significance of Y plus layer is, or what the significance of Y plus layer in modeling is. And as I mentioned, the Y plus in the end is not what we influence. We can influence the Y plus parameter not directly, but we can change the size, the height of the first element at the wall,
You can
and
give
that
it to
will
me
change
to answer.
Y plus. And as we told you, or we presented in the last 2 sessions, modeling the boundary layer is a very big challenge. And there are some models, for example, for some algorithms using for turbulence modeling. And when we, for example, use like in the in the homework assignment, K omega SST turbulence model, this is a turbulence model which requires a Y plus value below 200. And so I hope this answers your questions. Then there is a question, I think, for Akram. Which NACA airfoil is that? Is it an Appler E423?
For which model?
I think he's talking about the airfoil you showed at the beginning of your presentation.
I don't know, maybe this first model was just taken from the internet, so even there is no specification, so it's just NACA profile. But to say the truth, like the real number, I don't know. Like the one in this third slide, I'm not sure really which airfoil is it. So I know it's NACA 4-digit, but it was just to show you like the camber, the chord length, and some so the idea was not really to talk about the name of the airfoil, because imagine like I told you, like for every parameter you can change the number, so you will have infinity of profiles that you can generate with four parameters. So it's really difficult, and it's impossible to know that the profile just from here. So yeah.
Okay, but there's the next question, I think, which you should also answer, Akram. Simeon asked or said that he don't understand why you would relieve the high pressure on top using the louvers. Can you maybe answer this question?
The one of the rear wing?
Yes.
Oh, okay. So the idea behind using louvers is, like we know that the rear wing from the top side, we have really high pressure from the top side. And I'm not sure really here if I have a picture of the rear wing to explain this idea more, but of course we have this one.
Here we have a picture of a rear wing.
Yeah, yeah, we have already the model. So can you give me the control to my screen, please?
Yes, wait.
To show them 3D model and to explain this idea. Because to say the truth, it's a really important concept, and yeah. All right, so you can see my screen now.
Yes.
Okay, great. So we have here on the top side of the wing, I mean here in this region, the pressure is really high. And this pressure, like we talked the last time, when you have difference of pressure or large delta P, or not large, but if you have delta P and you have discontinuity, like you can see here in this sharp edge, you will have a strong vortex that will create. So the flow in this region will try to escape to this region, because here is approximately, the pressure is approximately atmospheric, and here it's too high, so this flow will try to go in this way and will create really strong vortex. The idea why we don't need vortices, so why the vortices are not good, because they create an induced drag. The idea behind induced drag is that this flow will create a downwash, and this downwash, it's like vector of velocity, and this vector of velocity will, I will not go more in details, but this vector of velocity will change the downforce vector, and this vector will have a component to drag. So they call it induced drag because it's like generated in a way by the downforce vector, and due to this velocity created by the vortices, so the downwash. Okay, and why we use these louvers or these slots here is to, because when you open these slots here, what you will do, you will like quantity of the air will go from here. Okay, so we will reduce the delta P, or the difference of pressure between here and here, and these have significant influence on the strength of this vortex. So this will really reduce the induced drag. So for this reason, they use the louvers. So the idea is just to reduce the delta P, or the pressure difference between the top side of the wing and the here from this side. And also, that's right, this will reduce a little bit in the drag. I mean in the downforce, because you will reduce some of the quantity of the pressure from the top of the wing. So you will reduce in the downforce, but we have said that it's more important the efficiency. So when we talk in aerodynamics, it's more important the efficiency. It's the ratio between downforce and the drag. So for this reason, if you open these slots, you will reduce the downforce, but in fact you will increase in your efficiency. So this is the concept behind louvers. I hope I have answered the question. Hello?
Hey, sorry, I just muted myself and it took me a second to
Okay, no problem.
unmute
It
me.
was the answer was okay?
Yes, for sure. Very good answer.
Okay,
I think it's quite complex but also important topic. Okay, then let's go further with the other questions. And okay, next question by Thomas again. Does CAESES user have to specify increments of investigation values for the design parameters, or is CAESES a true optimization that finds the optima automatically?
So the idea is, I'm not sure here if we will have something like, so I will like, you can see my screen now. Hello? Okay,
Yes, I can
so
see
the
your
idea, okay, perfect. So the idea here is, if you do optimization, so SOBOL is one of the design of the optimization algorithms. So here in the SOBOL, what you have, so if we go to design variables, so to get the design variable, it's just, I will take one of these parameters and create it as design variables. I don't know, maybe this one, and put it as design variable. And here, so we have this is a design variable. So the initial value for this design variable or parameter is 0.5. So you will create, so you will specify the lower bound and the upper one. Okay, and then using this optimization algorithm will take like arbitrary some values between these two bonds and will create different variables. And also there is a possibility, so here in the optimization here, there is a possibility to specify your step of increment. So your step of, so we will put this one, we'll move to this one with the step of 1 or and so on. Okay?
Yes, thank
So
you
this
very
is
much.
the idea.
Then there is a question about hardware requirements. What PC is suitable for SimScale about optimal RAM and processor? That's a very good question. Basically, for using SimScale, you don't need any specialized dedicated hardware. For sure, there are some minimal requirements, like you need to have a graphic card at least, which supports 3D and WebGL. And in general, I would say we recommend a minimum of 2 or 3 GB of RAM, a modern CPU not older than 5 years, and a graphic card which supports WebGL. Yes, and regarding the internet connections, you don't need a really fast connection. For sure, a faster connection makes some special things like post-processing faster, but for computation it has no influence. But in general, it is very important to have a stable and not too slow internet connection. Okay, then there is the next question by Manan. And he asked if you can re-explain the theory behind the meter surface technique.
All right, yeah, with pleasure. Okay, so you can see my screenshot? No, my screen, I mean.
Yes.
All right, perfect. Okay, so the idea behind the meta surface is we have. I hope you have understand the idea of the parameters, because like for every geometry have parameters to specify like the geometries that, like we have talked about this airfoil, so we have 4 parameters. We have the chord length, the camber position, and the thickness, maximum thickness. So these parameters are designed in the 2D plan. Okay, so to explain it more in a real case, so I will back here to this picture. So imagine like we will take section here in this upper element of the airfoil of this flap, and we will have a profile there, and this profile is characterized by a parameter. So let's say like I have already said, camber position, thickness, and so on. And like you can see here, if we look to the shape of this geometry of this flap, the distribution of these parameters are not the same along the span-wise or along this direction. So here what we do, we control our parameter with functions. Like you have seen this in the demo presentation. So this function, what did control the distribution of the parameter along the span-wise. And using this combination between the 2D profiles or the 2D parametric profile and the function that describe how this geometry is, how this parameter is described along the geometry, when you combine these two things, you will get a surface that is based on the 2D profile and the function that describe the behavior, how these parameters behave along the span-wise. So for example, if I will also back to the lab, to the cases. So here if you will see, just I will try to hit this one. Okay, so here you can see the profile of our model. So it's a profile that is characterized by a set of parameters. Like I have said this before many times, it's parameters that describe our geometry. Here it's the NACA 4-digit, it's the camber position, the chord length, and the thickness. So these parameters here need to be, so you have to describe how these parameters are distributed along this way, so along this way, the span of the wing, or along this path, so let's say along this way. And using these functions, what you will do, for example, if I will show my functions, for example, let's talk about this chord length. So if you see here this shape of the functions, and if you see the shape of the profile here, it's approximately the same, because what you say that at 0, so 0 it's here in the middle, here it's the 0, where is it? Just in the Y, so here it's the Y, so in the 0 you have this chord length. This chord length is this one, it's this height here, and at some point here you have moved this point down and you get this shape here. So this is the idea behind the meta surface. It's parameters that are connected to functions, then a surface is built based on these two things, so the parameter and the function. Of course, if you talk about the theory behind this, the theory is really complex, and me personally, I'm not in these things because it's more for a developer and these things, but the idea of creating this meta surface, it's this one, and of course, if you want to more details about how this technique works, so just if you download the free version of CAESES and you go here to tutorials, so tutorial you will have a lot of tutorials how to work with the freeform deformation, also with the meta surface, different things like the S-duct, like different thing, airfoils designs, and also you have samples where we have like already existing geometries and already existing models that we have created using CAESES, and you can open it and play around with the parameters and to understand more. So for example, I can suggest you to download the free version and open one of these models of the meta surface, and you can just move the functions and the parameters to understand more how the idea is behind this technique. Okay, I hope my question was helpful for you.
Yes, I thank you very much, Akram. Okay, guys, I know there are some more questions, but unfortunately, we're really running out of time. Yes, if your question was not answered yet or not specifically enough, please send us the email or write it into the forum, and then we will instantly answer your question. Thank you very much for joining us the last 3 weeks. It was really a big pleasure for me, and also I think for Akram to host this webinar series. I hope to see a lot of submissions for the homeworks, and yes, if you have any questions, just send us an email, reach out to us. Thank you very much. Have a nice week. See you soon. Bye.